Okay, so now we're going to describe Hamiltonian mechanics. And before we start, let me just give you what is the basic idea. So Newton's second law, remember, says mass times the acceleration is minus dv dx. Now, this is equal to 1 second order differential equation. Okay, so that's Newton's second law. We can rewrite it slightly. So because the mass is a constant, I can rewrite this as d by dt of m dx dt is equal to minus dv dx. And now I will define p to be m dx dt, okay? And then I can write Newton's second law as dp dt is equal to minus dv dx. And what you'll notice here, we have two first order differential equations. So we've gone from one second order differential equation to two first order differential equations. In fact, Hamiltonian mechanics is a way to systematically do this regardless of what system you're discussing. So that's the basic idea. We're going from one second order equation to two first order equations. So let's see, how does this work? Let's do this in general. So first of all, we need to define what we mean by P. We're not going to say that it's mx dot. We'll say that P is equal to dl dx dot. And this is our first important equation. So let's number it as 1, and we'll give it a box. Okay. We say that P is the momentum conjugate to x. So if somebody tells you to work out what is the momentum conjugate to x, you just calculate dl dx dot. Now, for many of the Lagrangians that you consider, equation 1 will just tell you that P is equal to mx dot, so exactly like we wrote above, but that's not always the case. For example, if you consider a charged particle coupled to an electromagnetic field, that's a very physical problem you might like to study. In that case, P is not simply equal to mx dot, okay? So the definition given in 1 of the conjugate momentum is more general than just saying P is equal to mx dot. Equation 1 always tells us what P is, no matter what problem you study. Now I'm going to introduce a new function called the Hamiltonian. The Hamiltonian depends on P and x, and it's given by Px dot minus the Lagrangian, which you know depends on x and x dot. And this we will call equation 2. It's also a very important equation. Now let's unpack this a little bit. You know, it looks a little unusual. Is it correct? I mean, h of p and x is px dot minus lxx dot. It looks like h does depend on x dot. So is equation 2 really correct? Well, let's work out what is dh dx dot. So remember, when we take this derivative, we treat p and x as constants. So when we differentiate the first term above, we'll just get p. And then we'll get minus, and now we need to differentiate the Lagrangian with respect to x dot. But the derivative of the Lagrangian with respect to x dot is just p. So we've got p minus p, which is 0. So indeed, the Hamiltonian does not depend on x dot. So that's a pretty remarkable property of this transformation that we're performing, and it's got a special name. It's called the Legendre transform. Now, I'm sure you've met it. Probably you've met it in classical mechanics, but you may also have met it in statistical mechanics. For example, when you are transforming between the Helmholtz free energy and the Gibbs free energy, things like that. What does the Legendre transform allow us to do? Well, this is the important thing. It allows us to transform between functions that depend on different variables. In this case, we've gone from the Lagrangian, which depended on x and x dot, to the Hamiltonian, which depends on p and x. So the Legendre transform allows us to change what variables our function depends on, and that's how we use it. Okay, good. What I'd like to do next is I'd like to derive some equations of motion. So the way I'm going to do it, let me take a look at what is dH. Well, I know that h depends on p and x. So first of all, it will be dH dx times by dx plus dH dp times by dp. Okay? So I calculated this variation using the left-hand side of equation 2. But now let me calculate the variation using the right-hand side of equation 2. So from the px dot term, I will get an x dot dp plus a p dx dot. Okay, so I've just varied the px dot, there's two terms, and now I can vary the Lagrangian. So I'll get minus dl dx times by dx minus dl dx dot times by dx dot. And I want to manipulate this a little bit. So I want to remove all reference to the Lagrangian. So first of all, I know that, I know that dl dx dot is equal to p. So I can use that inside this last term over here. I also know that dl dx is equal to d by dt of dl dx dot. I know that dl dx dot is p, so this is nothing but dp dt, and I can use that inside that term there. Good. So let's just write this down. This is equal to x dot dp plus p dx dot. Now let me use the red replacement. This is minus dp dt times dx. And for the last term, I've got minus p dx dot by the blue replacement. This is nice. So this dx dot term over here cancels against that dx dot term over there. And I like that because I know that the Hamiltonian should not depend on x dot. So dH should only depend on dp and dx, and indeed that's what I find. Now let me compare the two expressions that I've got for dH. First of all, I've got a term over here which is proportional to dp, and I've got a term over here which is proportional to dp. Comparing the two of them, I learn that x dot is equal to dH dp. And then if I compare the term proportional to dx over here to the term proportional to dx over here, I learn that dp dt is equal to minus dH dx. Okay, these are also important equations. So let me call this equation 3, and I'll box it. And let me call this equation 4, and I will box it. Equations 3 and 4 are called Hamilton's equations. Good. So let's take a look. We've got the basic equations now of Hamiltonian mechanics. We define the momentum conjugate to x as P is equal to dl dx dot. Then we define the Hamiltonian using the Legendre transform. And then we've managed to determine Hamilton's equations that are sitting at the bottom of the page. Okay, next thing that we're going to do is to check Hamilton's equations, but we'll do that in a moment.